There is a place in North Florida where the morning arrives slowly. It comes first as a pale suggestion of light through the cypress trees, filtering through the long Spanish moss that drapes from the branches like curtains left half open. The birds begin before the sun has cleared the horizon, a soft, patient chorus of ibis and herons, and the occasional cry of something distant and unseen moving through the wetlands. The air carries the smell of cool water and damp earth, the particular scent of a place where land and water have been negotiating with each other for a very long time. And then you hear it, or rather you feel it, the quiet movement of something large just beneath the surface of the ground, pressing upward, rising through limestone with the unhurried confidence of water that has been traveling for years. Wakulla Spring rests in the forest of North Florida like a secret that the land never quite managed to keep entirely hidden. On a calm morning, the water is so clear that it appears almost as though the spring itself does not exist, as though you are simply looking through a glass floor at the pale limestone 20, 30, 40 feet below the surface, undisturbed and patient and ancient. The spring pool stretches across several acres, its edges shaded by old-growth cypress and magnolia, the water so perfectly transparent that you can watch a fish turn lazily at the bottom and see the individual movement of its fins. The surface barely moves. Small ripples drift outward from the center of the spring, where the water rises continuously from somewhere far below, ascending through the earth as it has done since long before any human being ever stood beside it. The spring produces, on average, several 100 million gallons of water every single day, not as a flood, not as a surge, but as a constant, quiet, unhurried release. The water simply arrives. It has always arrived. It will continue arriving long after everything built around it has returned to soil. If you are the kind of person who finds peace in quiet places, in forests and still water and mornings that feel like they belong to no particular century, then you are welcome here. And if the idea of settling in for a gentle journey through one of Earth's oldest hidden landscapes sounds like the right way to spend a quiet evening, History's Sleepy Time would be honored to have you along. There is no urgency here, no rush toward any destination, only the slow, patient unfolding of a world that has been waiting a very long time to be understood. The water below Wakulla Spring is the color of pale blue glass on a cloudy day, not the tropical turquoise of shallow beaches, but something cooler and more complex, a blue that deepens gradually as the bottom falls away. The light from the surface reaches down in long, shifting columns bending gently with each movement of the water, above illuminating particles of dust and organic matter that drift so slowly through the water they seem almost to be floating in something thicker than water, something more like time itself made visible. The spring basin, at its deepest point near the main cave entrance, descends to approximately 180 feet below the surface. For much of recorded history, people assumed that the water emerging from Wakulla Spring simply rose from some large underground reservoir, a pool of water hidden somewhere in the rock, deep but finite, comprehensible. A person standing at the edge of this spring in 1800 or 1900, or even 1950, could have been forgiven for imagining that the mystery ended at the cave entrance visible at the bottom of the spring bowl, that the darkness beyond that opening led only a short distance before meeting solid rock. The truth, when it finally began to reveal itself to the people patient enough to descend and look carefully, turned out to be something considerably more extraordinary. The cave entrance at the bottom of Wakulla Spring is not the beginning of a small underground room. It is the opening to one of the largest known underwater cave systems in the world, a network of passages, galleries, and submerged tunnels that researchers have now traced for many miles in multiple directions beneath the Florida landscape, and which continues in dozens of directions. Beyond the limits of what any diver or instrument has yet been able to reach. This is not a system measured in hundreds of feet. It is measured in miles, in the particular language of cave diving surveys. Wakulla Spring connects to what explorers and scientists call the Wakulla Sinks Cave System, a network that, as of the most recent surveys available, extends for more than 35 miles of documented underwater passage, making it one of the longest underwater cave systems ever mapped in the Americas. 35 miles of passage beneath the ground, reached through a hole in the bottom of a quiet spring in the middle of a North Florida forest. And yet, despite those 35 miles of mapped passage, researchers believe that what has been explored represents only a small portion of the total system, that the passages extend far beyond the current reach of exploration, connecting to other springs, other cave systems, other portions of a geological formation so vast that it extends across the entire Florida peninsula and reaches into Georgia and South Carolina. Standing beside the spring on a quiet morning, watching the sunlight bend through the water toward that pale cave entrance far below, it is natural to find yourself asking a question that feels simple but opens into something much larger. How can a spring become the entrance to an underground world larger than many mountain ranges? The answer begins not with the spring itself, but with the stone beneath it, and with a chapter of Earth's history that unfolded so slowly across such enormous lengths of time that it is almost impossible to hold the full scale of it in the mind at once. But that is exactly where this journey must start. Far below the cypress trees, far below the transparent water, far below the pale floor of the spring, the limestone waits, cool and ancient and patient, holding within its layers the compressed memory of an ocean that existed long before Florida did. Before the forests arrived, before the rivers carved their courses, before any creature recognizable as modern walked across this peninsula, Florida did not exist in any form we would recognize today. What existed instead was an ocean. For tens of millions of years, the shallow tropical sea that covered what would eventually become Florida was rich with life. Coral polyps built slow, intricate structures across the seafloor. Mollusks, brachiopods, sea urchins, and countless varieties of marine organisms lived and died across the shallow continental shelf in numbers too vast to estimate. The waters were warm and clear, much like the tropical Caribbean seas of today, and the organisms that lived within them left behind when they died, something that would prove more important to the future of this region than anything that lived in the water above. They left behind calcium carbonate, the mineral material that forms the hard shells and skeletons of marine life. And as each generation of creatures died, as shells and coral and microscopic organisms sank slowly to the seafloor and accumulated there across millions of years of geological time, the weight of the layers above compressed those remains into something solid and pale and enduring. The result was limestone. Limestone is, in its most essential description, a sedimentary rock composed primarily of calcium carbonate, the compressed and mineralized remains of ancient marine life. It forms, characteristically, in shallow, warm, clear water, where marine organisms are abundant, and where the conditions allow those organisms to build and maintain their calcium-based shells and structures. The Florida that lies beneath the surface today is built almost entirely upon this material, a limestone platform of extraordinary thickness, in some places reaching depths of several miles below the current surface of the ground. Geologists refer to this as the Florida platform. It is an enormous geological structure, a broad, relatively flat mass of carbonate rock that extends not only beneath the visible peninsula of Florida, but continues for considerable distances beneath the surrounding ocean floor. The limestone layers that form the platform were deposited over an enormous span of geological time, beginning roughly during the Eocene epoch, approximately 34 to 56 million years ago, and continuing through subsequent geological periods, each depositing additional layers of marine sediment that were eventually compressed into rock. When you hold a piece of Florida limestone in your hand, you are holding something assembled from the accumulated lives of billions of marine organisms, creatures that built their shells grain by grain, atom by atom, absorbing calcium from seawater and incorporating it into their bodies, then releasing it back into the earth when they died. The stone is a library, in a sense, a record of life written in mineral and preserved across timescales that dwarf any human measure of history. But limestone has a particular quality that makes it unlike most other rocks, a quality that would eventually shape the entire hidden landscape beneath Florida in ways that no human observer could easily predict. Limestone dissolves, not quickly, not dramatically, not in the way that soft material crumbles under rain. But limestone, when it comes into prolonged contact with slightly acidic water, undergoes a gradual process of chemical dissolution that slowly, patiently, over thousands and millions of years, eats away at the rock and carves spaces where no spaces existed before. The chemistry of this process is elegantly simple. When rain falls through the atmosphere, it absorbs small amounts of carbon dioxide from the air, forming a weak carbonic acid, a solution so mild that it presents no danger to living things, but which, over geological timescales, is perfectly capable of dissolving solid limestone. As this slightly acidic rainwater seeps downward through cracks and joints in the limestone, it slowly widens those cracks, dissolving the surrounding rock and carrying the dissolved material away in solution. Year after year, century after century, millennium after millennium, the cracks become channels, the channels become tunnels. The tunnels become passages, The passages connect and branch and grow, following the path of least resistance through the stone, carving what geologists call a karst system, one of the most distinctive and architecturally complex geological formations that water is capable of creating anywhere on Earth. Florida is, by any geological measure, one of the premier karst landscapes on Earth. The combination of thick limestone formations, abundant rainfall, and a warm climate that promotes the biological production of carbon dioxide in the soil, which further acidifies the rainwater before it enters the ground, creates conditions almost perfectly suited to karst development. The result, accumulated across millions of years of geological history, is a landscape that is simultaneously ordinary in appearance and extraordinary in structure. From the air, much of North and Central Florida looks unremarkable: forests, wetlands, agricultural land, scattered lakes and rivers. The landscape is flat by the standards of almost any other American region. There are no dramatic peaks, no deep visible canyons, no obvious signs that the ground beneath has been carved into something vast and complex. Florida's extraordinary landscape is one that almost entirely conceals itself from view. But the evidence of karst geology is visible if you know how to look for it. The thousands of natural lakes scattered across the Florida peninsula, including many that appear quite suddenly in the landscape without any obvious surface drainage, are, in large numbers, the surface expressions of karst dissolution. They exist where the limestone beneath has dissolved significantly enough to create depressions that collect and hold water. Sinkholes, which occasionally appear with dramatic and sometimes alarming suddenness beneath roads, homes, and fields, are the most sudden expression of this same process. Places where the slow dissolution of limestone has eventually created a void so large that the ground above can no longer support its own weight and collapses inward. Throughout North and Central Florida, sinkholes open with a frequency that reflects just how actively karst processes continue to reshape the landscape today. These are not geological relics of some distant past. They are evidence of an ongoing conversation between water and limestone that has been proceeding for millions of years and shows no sign of concluding. The caves, passages, and tunnels that form within karst limestone systems like the Florida platform are created through exactly this process, but expressed over far longer timescales and far greater depths. As water dissolves pathways through the limestone, it gradually creates interconnected networks of passages that can extend for enormous distances, connecting recharge areas at the surface where water enters the ground with springs where the water eventually returns to the surface, sometimes after traveling many miles through the rock. The marine fossils preserved within Florida's limestone layers serve as a quiet reminder of how thoroughly the history of this peninsula has been shaped by the sea. Researchers occasionally find the remains of ancient marine organisms, shells, coral fragments, and the mineralized traces of creatures that lived and died in warm Eocene and Oligocene oceans, preserved in the walls of caves, in exposed road cuts, and in quarry excavations across the state. These fossils are not particularly rare in Florida. They are, in fact, a routine feature of the limestone geology. But each one represents, in miniature, the story of how the ground beneath Florida was assembled, one organism at a time, across incomprehensible lengths of time, in a warm, shallow sea that no longer exists. The Florida that tourists visit and that millions of residents call home rests upon this foundation, an enormous mass of ancient marine limestone, slowly and quietly being shaped by the water that moves through it, carrying the dissolved memory of ancient seabeds toward the springs and rivers of today. And somewhere within this vast limestone formation, in the network of passages and conduits that connect the rainfall of North Florida to the crystal-clear springs that emerge across the landscape, lies a hydrological system so large and so important that it quietly sustains the lives of tens of millions of people, without most of them ever pausing to consider that it exists. The question that forms naturally from all of this is one that seems almost too large to hold, and yet it follows inevitably from everything the limestone suggests about the nature of the water moving through it. If the rain that falls across an entire region can dissolve passages through solid rock across millions of years, where does all of that water go, and how does it travel from where it falls to where it finally emerges? That question leads somewhere specific, somewhere ancient and immense, and almost entirely hidden from view. Water, given enough time, will find its way. This is not a metaphor or a philosophical observation. It is a precise description of how groundwater actually behaves within a karst limestone system. Water does not choose its path in the way that a deliberate traveler might consider alternatives. It simply responds to the physics of its situation, moving in the direction of lower pressure, following existing cracks and conduits, dissolving new pathways when existing ones narrow, and always moving downward and outward towards some eventual exit. Beneath Florida, this process has been operating continuously for millions of years. The result is a groundwater system of such enormous scale that it ranks among the most significant freshwater formations on the North American continent. The Floridan Aquifer system is one of the most productive and extensive aquifer systems in the world. It underlies an area of approximately 100,000 square miles, extending beneath the entire state of Florida and into portions of Georgia, South Carolina, and Alabama. In thickness, the aquifer reaches many hundreds of feet in some areas, a vast underground reservoir of fresh water held within the pores, fractures, and conduits of ancient limestone. The word aquifer sometimes conjures the image of an enormous underground lake, a still, dark pool of water sitting quietly beneath the earth, waiting to be accessed by a well. This image, while understandable, does not accurately reflect how the Floridan aquifer actually functions. The aquifer is not a static reservoir of standing water. It is a dynamic, actively flowing system of groundwater moving through the connected spaces within the limestone, through microscopic pores between grains, through fractures and joints in the rock, and through the larger conduits and passages that karst dissolution has carved across millions of years. In the portions of the aquifer where conduit flow is most developed, where the karst passages have grown large enough to allow water to move freely through them, The groundwater behaves less like water seeping slowly through solid rock and more like a true underground river. It flows. It has direction and velocity. It carries dissolved minerals and suspended material from one location to another, and it emerges, eventually, at locations where the pressure of the water column above forces it back to the surface, at springs, seeps, and other discharge points scattered across the Florida landscape. Florida has more freshwater springs than any other state in the United States, and more than any other comparable region on Earth. There are more than 1,000 individual springs identified across the state, ranging from small seeps that produce only a trickle of water to enormous first-magnitude springs that discharge hundreds of millions of gallons per day. These springs are not independent features of the landscape. They are all connected, to varying degrees, to the same vast underground system, emerging at different points along the same broadly interconnected network of groundwater flow. Wakulla Spring is among the most prolific of these, a first-magnitude spring that consistently ranks among the highest flow springs in the state, discharging water that has traveled through the Floridan Aquifer from recharge areas many miles to the north and east. The water that rises through Wakulla Spring may have entered the ground as rainfall weeks or months or even years before it arrives at the spring. The exact travel time depends on the specific pathway the water follows through the aquifer. And this is something that researchers continue to study and refine with each new generation of monitoring technology. The recharge zones, the areas where rainfall enters the aquifer from the surface, are largely concentrated in the north-central portion of Florida and in adjacent areas of Georgia, where the limestone formations are exposed at or near the surface, and where the thin, permeable soils allow water to percolate downward readily. In the karst terrain of this region, rainfall does not simply run off into streams and rivers the way it does in areas underlain by impermeable rock. Instead, much of it disappears directly into the ground, swallowed by sinkholes, seeping through the soil, descending through fractures in the limestone until it reaches the saturated zone of the aquifer below. Once within the aquifer, the water begins its journey toward discharge. The direction of flow is broadly from areas of higher hydraulic head, essentially areas where the water table is relatively high and the groundwater is under greater pressure, toward areas of lower head where the pressure is reduced and the water seeks an exit. In the portion of the aquifer that feeds Wakulla Spring, the general direction of groundwater flow is toward the south and southwest, moving through the limestone from recharge areas in the highlands of North Florida toward the spring itself, which sits at a point where the artesian pressure of the water column below is sufficient to force the water upward and out of the ground. The term artesian refers specifically to this condition, groundwater under sufficient pressure to rise on its own without pumping. The Floridan Aquifer is, in many areas, a confined aquifer, meaning that the water-bearing limestone layers are overlain by less permeable rock or sediment layers that confine the water under pressure. When a well penetrates this confined layer, or when a natural opening exists in the confining layer, such as at the bottom of Wakulla Spring, the pressurized water rises upward, emerging at the surface as a spring. The conduits that carry the greatest volumes of water through the aquifer toward Wakulla Spring are, in essence, the structural skeleton of the cave system that divers have been slowly mapping since the mid-20th century. These are not small cracks in the rock. The major passages of the Wakulla sink system are in many places large enough to navigate with full diving equipment, with ceiling heights in some galleries reaching 20 or 30 feet above the diver's position. The cave is, in its physical dimensions, an underground landscape, a world of enormous proportions that happens to be entirely filled with water. The Wakulla Sink's cave system takes its name from the connection established by cave divers working in the 1980s and 1990s. Between Wakulla Spring and a series of surface expressions of the same cave system located in nearby Leon Sink's geological area, a preserve where the karst landscape is expressed in dramatic fashion at the surface, with numerous sinkholes disappearing streams, and small lakes that mark the locations where the cave system below intersects with the surface of the earth. This connection between the distant, quiet sinkholes of Leon Sinks and the brilliant, open pool of Wakulla Spring represents one of the longest underwater cave connections ever established in North America. It was confirmed not through a single dramatic discovery, but through the patient, methodical work of cave diving teams who surveyed passage after passage, laid guideline after guideline, and gradually assembled a picture of a system far larger than anyone had initially imagined. The water that flows through this system does not announce itself. It moves quietly in the permanent darkness of the cave, with a velocity that varies from one passage to another, faster in the tighter conduits where the flow is concentrated, slower in the larger chambers where the same volume of water spreads across a greater cross-section. Researchers studying the water chemistry at Wakulla Spring find a consistent temperature of approximately 68 degrees Fahrenheit, maintained by the Earth's internal warmth at that depth, essentially constant regardless of the season, the weather above, or the temperature of the air outside the spring. This constant temperature is one of the aquifer's most distinctive qualities. The water of the Floridan Aquifer does not experience seasons. It does not know whether the cypress trees above are bare or full. It does not register the warmth of summer or the occasional cold of a North Florida winter. It exists in a condition of geological stability, a thermal equilibrium established by the depth and the mass of rocks surrounding it that has remained essentially unchanged for as long as the aquifer has existed. This consistency makes the aquifer a remarkable record keeper. The chemical composition of the groundwater, its dissolved mineral content, its isotopic ratios, its biological properties, carries information about the conditions under which the water entered the ground, how long it has been traveling, and what it has encountered along the way. Researchers studying aquifer chemistry are, in a sense, reading a continuously updated record of the hydrological conditions across an entire region. A record written not in words, but in dissolved atoms and carefully measured molecular ratios. How the water enters the ground, how it moves through the limestone, and how it finally emerges at the spring. This is the fundamental story of the Floridan Aquifer. But before scientists developed the instruments and techniques to begin reading that story, other people came to stand beside the springs of Florida, and they understood the water in ways shaped not by chemistry or geology, but by long familiarity, cultural tradition, and a relationship with this landscape measured not in centuries, but in millennia. Long before the limestone had a name, long before any instrument existed to measure the depth of the water or the distance of its underground journey, people came to stand beside the springs of North Florida and found in them something essential. Not simply water, though water, in the most practical sense, is always what a spring offers first. Something more than that. Something that comes from the particular quality of a place where the earth gives freely and continuously, where the water is always cool and always clear, where the temperature never changes and the flow never stops. A reliability so complete, across so many generations of human experience, that it must have seemed less like geology and more like a kind of promise. The archaeological record of human presence near Florida's freshwater springs is one of the oldest and most carefully studied in the eastern United States. Researchers working at sites around Wakulla Spring and other major springs across the Florida peninsula have found evidence suggesting that people have been drawn to these locations for at least 12,000 years, and possibly considerably longer. Though the deeper layers of the archaeological record remain difficult to access and interpret with precision. The earliest inhabitants of Florida arrived during a period geologists call the Pleistocene epoch, the last great ice age, when global temperatures were substantially lower than today, sea levels were significantly reduced, and the Florida peninsula was both larger and considerably drier than it is in the present. During this period, the springs that exist today were among the most reliable sources of fresh water across a landscape that was otherwise considerably more arid than the subtropical Florida we know now. Springs do not depend on seasonal rainfall. They flow because of the pressure within the aquifer far below, a pressure maintained across geological time regardless of surface conditions. In a dry landscape, a spring is a permanent fixture of extraordinary value. Archaeological investigations in and around Wakulla Spring have recovered remarkable materials from the spring basin itself, the result of the spring serving not only as a water source, but as a site of human activity across many thousands of years. Mastodon bones have been found in the sediments of the spring, along with the bones of giant ground sloths, horses of an extinct species, and other megafauna of the Pleistocene that shared the Florida landscape with the earliest human inhabitants of the region. These fossils, preserved in the cool, oxygen-poor environment of the spring basin, represent some of the most significant Pleistocene paleontological material recovered from the American Southeast. The relationship between these early peoples and the animals whose remains appear in the spring is a matter of ongoing scholarly study and careful interpretation. Researchers have debated whether the presence of megafauna bones in the spring reflects hunting activity by early human inhabitants, whether the animals came to the spring on their own and died there naturally, or whether some combination of these and other factors contributed to the accumulation. Current evidence does not definitively resolve this question, and researchers continue to refine their understanding of the archaeological record at Wakulla and similar sites across Florida. What the evidence does suggest, clearly and consistently, is that the springs of Florida were central features of the landscape for the people who inhabited this region across thousands of years of prehistory. The Paleo-Indian peoples who first occupied Florida, broad cultural categories representing diverse communities of hunter-gatherers, adapting to a changing landscape across many generations, found in the spring's reliable water a focal point for animal activity, and likely a degree of social significance that researchers are only beginning to appreciate fully. As the Pleistocene gave way to the warmer and wetter Holocene, the geological epoch in which we still live today, the Florida landscape changed substantially. The large megafauna disappeared, for reasons that remain debated among paleontologists and archaeologists, but likely involved some combination of climate change and the pressures of human hunting. The sea level rose, reducing the size of the Florida peninsula and transforming the character of many coastal and interior environments. The forests and wetlands familiar to us today gradually established themselves across the landscape. Through all of these changes, the springs continued to flow, and the people who lived near them adapted, generation by generation, developing cultures and traditions shaped by their specific environments, including the remarkable freshwater springs that punctuated the landscape of North and Central Florida. By the time European explorers first encountered the indigenous peoples of Florida in the 16th century, the region was home to a number of distinct cultural groups with long-established traditions and deep relationships with their local landscapes. The Appalachians, whose territory encompassed much of the Tallahassee region and the surrounding areas, including the Springs country of what is now Wakulla County, were among the most organized and culturally sophisticated of Florida's indigenous peoples at the time of European contact. They maintained productive agricultural systems, established towns, conducted extensive trade networks, and had developed complex social and ceremonial traditions over many generations of life in this particular landscape. The specific meanings and traditions that the Appalachians and their predecessors attached to the springs of their territory are not fully documented in the historical record, and researchers are careful to avoid projecting assumptions onto communities whose inner lives and beliefs are accessible only partially and imperfectly through the surviving evidence. What can be said with reasonable confidence is that freshwater springs were significant landscape features for the indigenous peoples of Florida. They appear consistently near archaeological sites. They were important sources of water for communities living nearby, and they occupy a prominent place in the geography of areas with known indigenous settlement. It is worth pausing here to acknowledge something that the archaeology of Florida's springs quietly reminds us, that the landscape we tend to think of as natural or unchanged has, in fact, been a human landscape for an extraordinarily long time. The cypress trees around Wakulla Spring, the particular arrangement of the wetlands and forests, the animals that live within the spring ecosystem today, all of these exist within a context shaped, to varying degrees, by thousands of years of human presence and human decision-making in this place. The springs were not discovered by European explorers. They were part of a world that had already been known and inhabited and understood, in ways different from modern scientific understanding, but no less real for longer than most recorded history extends. When Spanish explorers moved through North Florida in the 16th and 17th centuries, they encountered indigenous settlements near the springs and described the landscape in the terms available to them, noting the extraordinary clarity of the water, the abundance of fish and wildlife, the reliability of the flow. The Spanish established missions across the Appalachee Territory, including several in areas close to the springs of what would eventually become Wakulla County. And the documentary record of their observations provides historians with glimpses of the landscape during a period of profound and largely devastating change for the indigenous peoples who had known it for so long. The Appalachee population collapsed dramatically during the colonial period, the result of epidemic disease, warfare, enslavement, and displacement that destroyed in a matter of generations a culture that had developed across millennia. By the early 18th century, following a devastating raid by English colonial forces and their indigenous allies in 1704, the Appalachee as a cohesive cultural and political entity had largely ceased to exist in their Florida homeland. Survivors scattered, some eventually resettling in other regions. The landscape they had inhabited for so long was gradually absorbed into the colonial frontier, its springs, its forests, and its underground waterways continuing their patient existence without reference to the political and human catastrophes occurring at the surface. The springs themselves did not change. The water continued rising from the aquifer, cool and clear and constant, carrying within it no memory of the civilizations that had grown and changed and suffered beside it, only the quiet chemical record of its own long journey through limestone. In the generations that followed, naturalists and explorers who came to examine the springs of Florida were often struck by a quality of the water that resisted simple description. The clarity was remarkable, not the clarity of a clean pool or a filtered aquarium, but something more fundamental, a transparency so complete that the water seemed almost to disappear, leaving only the view of whatever lay beneath it. Early accounts of Florida's springs frequently returned to this quality, reaching for comparisons that could convey to readers who had never seen such a place what it meant to look down through 30 or 40 feet of perfectly clear water and see the bottom as sharply as if you were standing in open air. William Bartram, the American naturalist who traveled extensively through the American Southeast in the 1770s and produced one of the most celebrated natural history accounts of the colonial period, described Florida's springs in terms of genuine wonder, noting the extraordinary clarity, the abundance of fish visible in the water, and the remarkable character of a landscape shaped so profoundly by the emergence of groundwater from the earth below. Bartram's observations made nearly 2.5 centuries ago, describe a spring environment not entirely unlike what visitors to Wakulla and similar springs can still experience today. A continuity that speaks to the remarkable resilience of these ecosystems when they are given the conditions necessary to maintain themselves. Yet even Bartram, with all his careful naturalist's attention to the details of the landscape, could not have guessed at the true scale of what lay beneath the springs he observed. The passages that carry water to the surface. The network of conduits extending for many miles in multiple directions through the limestone, the biological communities living in permanent darkness far beneath. All of this was entirely invisible to him. And to everyone else who stood beside the springs for the century and a half that followed his travels. Understanding what lay beneath would require not only the development of new scientific knowledge, but the invention of entirely new ways of going to look. And that required people willing to descend into a world that no previous generation had entered, equipped with technology that barely existed yet, guided by a curiosity patient enough to move slowly and carefully through darkness where no map had ever been drawn. The first divers who descended into Florida's underwater caves were not, for the most part, scientists. They were people moved by a combination of curiosity and a particular quality of temperament, a calm willingness to enter enclosed spaces filled with water, to move carefully in the dark with limited air, and to find in that experience not fear, but a kind of deep, quiet attention. Cave diving, as a systematic practice, emerged in the mid-20th century as recreational scuba diving itself became more widely accessible. The development of the self-contained underwater breathing apparatus, the aqualung, introduced to the public most prominently through the work of Jacques Cousteau and Émile Gagnon in the 1940s, transformed the relationship between humans and the underwater world. For the first time, a person could breathe underwater for extended periods without being connected to the surface by an air supply. The possibilities this opened were, to those with the temperament to pursue them, vast Florida's springs attracted divers almost immediately as the sport became more widely practiced. The extraordinary clarity of the spring water made underwater visibility far superior to that of the ocean or most freshwater lakes. A person floating at the surface of Wakulla Spring on a calm day could see the cave entrance at the bottom with remarkable clarity. And the cave entrances, visible from the surface, were naturally compelling to those whose curiosity ran toward the unknown. The early history of cave diving in Florida's springs is also, unfortunately, a history of losses, of people who entered underwater caves without adequate training, equipment, or understanding of the particular demands of that environment, and who did not return. The confined spaces of underwater caves present challenges that open water diving does not, the impossibility of ascending directly to the surface when air runs low, the potential for silt disturbed by a diver's movements to reduce visibility to near zero in seconds. The complexity of navigation in branching passages where the path back to the entrance can become dangerously unclear. The diving community in Florida responded to these tragedies by developing, over several decades, an increasingly rigorous set of training standards, equipment requirements, and procedural guidelines specifically designed for cave diving. The principles that emerged from this process, including the rule of thirds for gas management, which requires divers to reserve 2/3 of their air supply for the return journey before turning back, the mandatory use of continuous guideline from the cave entrance, and the requirement for multiple independent light sources, transformed cave diving from an activity of considerable risk into one that, practiced properly, could be conducted with a meaningful margin of safety, even in very challenging conditions. Among the figures who shaped this discipline, both through his explorations and through his extensive writing on technique and safety, was a cave diver from Florida named Sheck Exley. Exley was, by any measure, one of the most accomplished underwater cave explorers of the 20th century, a careful, methodical, and deeply experienced diver who approached the underground world with a combination of genuine curiosity and patient, systematic attention to the details of safety and procedure. Exley began cave diving in the late 1960s and spent the following decades exploring the underwater caves of Florida and later expanding his activities to systems around the world. He was instrumental in developing and documenting many of the safety principles that came to define responsible cave diving practice, and he contributed enormously to the scientific understanding of Florida's underwater cave systems through his careful documentation of the passages he explored. At Wakulla Spring, Exley was among the first divers to push deep into the cave system, exploring passages extending hundreds of feet from the entrance at depths that required careful management of both time and breathing gas. His explorations at Wakulla and other North Florida springs in the 1970s and 1980s established much of the foundational knowledge of the cave's structure and extent, and his records of the passages he surveyed provided the starting point for the more systematic scientific expeditions that would follow. In 1987, a scientific expedition to Wakulla Spring brought together a remarkable combination of cave diving expertise, geological science, and emerging technology in a project that represented one of the most ambitious underwater cave investigations attempted to that point. The Wakulla Springs Project. Conducted under the organizational leadership of Bill Stone, an engineer and cave explorer with extensive experience in both expedition caving and the development of technical diving equipment, deployed a team of highly experienced cave divers to systematically survey the cave system extending from the spring. Bill Stone was, and remains, a figure whose contribution to the exploration of underground environments extends well beyond any single expedition. Trained as a structural engineer, Stone applied the discipline and systematic thinking of his professional background to the challenges of deep cave exploration, developing new equipment and techniques specifically designed for the demands of pushing the limits of known cave systems. His work at Wakulla represented one of the first applications of what would later be called rebreather technology to cave diving, a form of breathing apparatus that recycles exhaled gas rather than releasing it. dramatically extending the time a diver can remain underwater on a given supply of breathing mixture. The 1987 Wakulla Springs project produced a detailed survey of the cave system extending from the spring, mapping passages, measuring depths, recording the physical characteristics of the cave environment, and establishing the spatial relationships between different portions of the system. The results confirmed what Exley and other early explorers had begun to suggest, that the cave beneath Wakulla Spring was not a simple linear tunnel, but a complex branching network of passages extending in multiple directions at varying depths, with connections to other portions of the regional cave system that raised the possibility of a system far larger than anything yet explored. A subsequent major expedition in 1999, again organized with Bill Stone's involvement and incorporating even more advanced technology, including an early autonomous underwater vehicle designed to survey portions of the cave too deep or too complex for divers to reach safely, extended the mapped extent of the system significantly, and provided the first glimpses of passages lying beyond the reach of conventional diving equipment. The experience of moving through the cave as a diver is, by the accounts of those who have done it, profoundly unlike any other form of exploration. The water in the Wakulla cave system is, in the portions closest to the spring entrance, extraordinarily clear, a visibility that allows a diver to see for many tens of feet in all directions. The cave walls are pale limestone, smooth in some places where the water has flowed over them for long ages, rougher in others where dissolution has left irregular surfaces. The passages range from broad galleries with high ceilings to narrower conduits, where the diver must move more carefully. And the scale of the cave in its larger sections is genuinely difficult to convey. An underground space of architectural proportions, entirely silent, entirely dark, beyond the reach of a diver's lights, entirely removed from any reference to the surface world above. Divers who work in these systems describe a quality of focused, quiet attention that the environment requires. Movement must be slow and deliberate. Stirring up sediment reduces visibility rapidly and can disorient a diver in a space where orientation is already challenging. Navigation depends on the continuous guideline, followed with careful attention, knowing that the line leads back to the entrance and that departing from it without very specific preparation is not a thing to be done casually. Everything in the cave environment rewards patience and penalizes haste. In this way, the divers who work in underwater caves have learned to move through the underground world in something like the way that water itself moves, slowly, carefully, following the available passages, measuring every action against the resources available for the return. The relationship between these explorers and the cave is not one of conquest. The cave does not yield itself to boldness or determination in the way that mountain peaks are sometimes described as yielding to climbers. It yields, if yield is even the right word, to patience, to the slow accumulation of careful observations, to the methodical deployment of guidelines and survey instruments, to the willingness to return again and again to a place whose full extent no single expedition could ever hope to reveal. And what the cave contains, beyond the geological record of the limestone and the hydrological story of the water, raises questions that bring the underground world into entirely different territory. Questions about life, about adaptation, about what a living creature does when the most fundamental condition of nearly all surface life, sunlight, is simply absent. Consider, for a moment, what darkness truly means underground. Not the darkness of a room with the lights off, where your eyes eventually adjust to a background of ambient light seeping beneath doors and around curtains. Not the darkness of a night outdoors, where stars and moon provide at least some gradation of light and shadow. The darkness of an underwater cave, in the passages beyond the reach of any surface light, is a darkness of a different kind entirely, a complete, total, permanent absence of any photon of light whatsoever. In this darkness, the concept of a daily cycle does not exist. There is no morning or evening, no change of seasons, no signal from the outside world that time is passing in any particular way. The temperature remains constant, that steady 68 degrees maintained by the Earth's own warmth, unchanging regardless of what is happening above. The water flows as it has always flowed, through the passages it has carved through the limestone over millions of years. And yet, life is here. The discovery that elaborate biological communities exist in the underwater caves of the Floridan Aquifer is one of the more quietly remarkable contributions of cave biology to our understanding of life's adaptability. The organisms found in these systems have not simply tolerated the conditions of total darkness and isolation from the surface world. They have adapted to them over many thousands of generations, developing physiological and behavioral characteristics specifically suited to an environment that, from the perspective of most surface-adapted organisms, would seem fundamentally inhospitable. Among the most studied inhabitants of Florida's underwater caves are the various species of cave-adapted invertebrates, small crustaceans, and other aquatic organisms that live in the water column and in the thin film of organic material that accumulates on the cave floor and walls. Many of these organisms are members of groups known as amphipods and isopods, small, shrimp-like creatures related to the familiar crustaceans of surface freshwater environments, but modified by long evolutionary isolation in the cave environment in ways that tell a clear story about how life adjusts to its circumstances. Cave-adapted crustaceans found in Florida's aquifer systems typically display several characteristics that distinguish them from their surface-dwelling relatives. Most have lost their eyes, or more precisely, have retained only vestigial structures where eyes once existed, small developmental remnants of a sensory organ that serves no purpose in an environment where there is no light to detect. Eye development is metabolically costly. It requires the investment of biological resources in tissue that provides no benefit in total darkness, and natural selection across many generations in the cave environment has tended to reduce this investment in cave-adapted populations. In place of vision, many cave crustaceans have developed enhanced sensitivity in other sensory systems, longer antennae and sensory hairs that detect chemical signals and mechanical disturbances in the water, with greater precision than their surface relatives. They navigate and locate food through a heightened awareness of the water around them, finding in chemical gradients and subtle vibrations the information that surface-dwelling relatives gather through sight. The biological communities of underwater caves operate on a fundamentally different energetic basis from surface ecosystems. Surface ecosystems are typically driven by photosynthesis, the process by which plants and algae convert sunlight into biological energy, forming the foundation of the food web that supports all other life. In caves, sunlight does not reach, and photosynthesis cannot occur. The energy base of cave ecosystems must come from somewhere else. In the underwater caves of the Floridan Aquifer, organic material enters the cave environment from multiple sources. Some is carried in by the water itself, a dissolved and particulate organic matter that enters the aquifer through recharge zones and travels underground with the groundwater, arriving in the cave passages as a dilute but continuous supply of energy. In areas close to the spring entrance, where some light penetrates, algae and other photosynthetic organisms can establish themselves, providing an additional energy source for organisms living in the transition zone between the lit and unlit portions of the cave. But perhaps the most interesting energy source in the deepest portions of cave ecosystems is one that operates entirely independently of sunlight. The communities of microorganisms, primarily bacteria and archaea, that derive energy from chemical reactions rather than from light. These chemolithotrophic organisms, a term meaning, essentially, organisms that feed on rock chemistry, can extract energy from the oxidation of compounds such as hydrogen sulfide, iron, or manganese present in the groundwater and in the surfaces of the cave walls. In this way, the deepest and most isolated portions of Florida's underwater cave systems support biological communities whose ultimate energy source is not the sun, but the chemistry of ancient limestone and groundwater, a form of life so thoroughly independent of the surface world that it represents in miniature a demonstration of how fundamentally life can adapt when the conditions of surface existence are simply not available. The cave-adapted organisms of the Floridan Aquifer are not merely biological curiosities. Many of them are found nowhere else on Earth, species that evolved in the specific conditions of particular cave systems and that exist only in those places. These are, in the precise scientific meaning of the term, endemic species, organisms whose entire global range is limited to a single cave system, a single portion of a cave system, or in some cases, a single spring or well. The number of such species associated with Florida's cave systems is substantial and continues to grow as biological surveys become more systematic and more thorough. The Florida cave crayfish, Procambarus pallidus, is one example of a cave-adapted species associated with the springs and caves of North Florida. Pale in coloration, with reduced eyes, this species occupies cave and spring environments where it would not naturally encounter the same pressures of predation and competition that shape the behavior and appearance of its surface relatives. Researchers studying cave crayfish and related species have found them to be long-lived relative to surface-dwelling crayfish, an adaptation consistent with the observation that cave environments, while energetically limited, are also relatively stable and free from many of the seasonal and climatic pressures that affect surface organisms. The Georgia blind salamander, Eurycia wallacei, is another remarkable example of cave adaptation found in association with the Floridan Aquifer system. This small, slender salamander lives its entire life in the groundwater environment, in springs, caves, and wells, and has adapted over many generations to the conditions of aquifer life. It is unpigmented, with reduced eyes, and depends entirely on the invertebrate community of the cave environment for its food supply. Like the cave crustaceans, it represents an evolutionary trajectory shaped entirely by the specific conditions of the underground world. What is perhaps most striking about these cave-adapted organisms is how thoroughly they reflect the geological history of the aquifer itself. Many cave species in the Floridan Aquifer are thought to have diversified from surface-dwelling ancestors during periods when the aquifer system was more directly connected to surface habitats, perhaps during past periods of lower sea level or different hydrological conditions, and subsequently became isolated in the cave environment as conditions changed. The genetic distances between cave populations and their nearest surface relatives, measured by modern molecular techniques, can suggest how long a population has been isolated in the cave, a kind of biological clock that records, in DNA sequences, the passage of evolutionary time underground. In this way, the biology of the cave is a kind of archive. Like the limestone itself, it preserves a record of history in forms that require patience and specialized knowledge to read. The organisms living in the permanent darkness of the aquifer are not simply surviving in a difficult environment. They are the living record of thousands of years of evolutionary change, driven by the specific conditions of a place most people never see and never think about, a place beneath the ground where water moves through limestone in the dark, carrying with it the chemistry and the life of an underground world of extraordinary quiet complexity. The cave fish, the pale crustaceans, the chemotrophic bacteria on the cave walls, all of them exist in a kind of suspended relationship with the geological and hydrological forces that created their world. They neither know nor need to know what moves above the limestone, what forest grows above the spring, what season shapes the surface world. Their world is the water, the stone, the slow chemistry of the underground, and the quiet current that has carried life through these passages for longer than any written record reaches. The question that arises from all of this, from the biology, the geology, the hydrology, and the exploration, is not simply how large the cave system is, though that question remains genuinely and fascinatingly open. The deeper question is how something so large and so biologically rich can remain, even today, so incompletely known. How do you map a river that exists entirely beneath the earth? There is a particular kind of patience required to map something you cannot fully see. On the surface of the earth, cartography, the art and science of making maps, has always depended, at its most fundamental level, on the ability to observe the landscape from some useful vantage point, a hilltop, a tower, eventually an aircraft. Eventually, a satellite orbiting hundreds of miles above the ground. The development of aerial and satellite photography transformed mapmaking in the 20th century by allowing cartographers to see the surface of the Earth from perspectives that revealed patterns invisible to observers standing within the landscape itself. The precise course of a river, valley, the boundary of a forest. The geometry of geological formations stretching across hundreds of miles. None of these approaches work underground. In an underwater cave, there are no hilltops, no aircraft, no satellites. The diver moves through the cave at the level of the cave itself, surrounded on all sides by stone, with visibility limited to the reach of a handheld light in water that, even when exceptionally clear, limits meaningful observation to a few tens of feet in any direction. The passages branch and reconnect in 3 dimensions, ascending and descending, narrowing and widening, connecting to other passages in ways that cannot be understood from within any single section of the cave. The challenge of representing this environment accurately on a 2-dimensional map, or even a 3-dimensional model, is one that requires both considerable technical skill and a very particular kind of systematic patience. The foundational tool of underwater cave mapping is the survey line, a continuous physical guideline, typically made of heavy monofilament or braided line, that is fixed to the cave wall at the entrance of the cave and extended through every passage as exploration proceeds. This line serves 2 purposes simultaneously. It provides a navigational reference, a physical path that a diver can follow back to the entrance regardless of how severely visibility has been reduced by silt or other disturbance. And it serves as the physical baseline along which survey measurements are taken. Cave diving surveyors working along a guideline take systematic measurements at regular intervals, recording the compass bearing of each section of line, the depth of the water at each station, and the distance from one station to the next. By accumulating these measurements across many dives and many passages, surveyors can gradually reconstruct the 3-dimensional geometry of the cave, calculating the position of each survey station relative to all the others, and building a progressively more complete picture of how the passages relate to one another in space. This process is painstaking in a way that is difficult to fully convey. A single survey dive might extend the known map by only a few hundred feet of passage, depending on the complexity of the terrain and the time available on the breathing gas supply. Passages that branch require separate survey dives for each branch. Passages that reconnect, creating loops in the cave system, require careful survey work to establish exactly where and how the connections occur. Areas where the cave becomes too low or too narrow for a diver to pass with standard equipment may require specialized techniques or equipment before they can be surveyed at all. The results of this patient, incremental work accumulate over years and decades rather than days or weeks. The map of the Wakulla Spring cave system that exists today, with its more than 35 miles of documented passage, was not the product of any single expedition or any single season of diving. It is the accumulated result of many hundreds of individual dives conducted by many different divers over several decades, each contributing a portion of the total picture, each building on the work of those who came before. The survey data collected by cave divers is processed and compiled into maps using increasingly sophisticated techniques. In the early decades of cave diving exploration in Florida, maps were drawn by hand, compiled from field notes taken underwater using wax pencils on plastic survey slates, then translated into plan views and profile views that showed the horizontal layout and vertical extent of the cave passages respectively. These hand-drawn maps, produced with considerable care and skill, represent an important historical record of the exploration of Florida's caves and remain valuable reference documents even as more sophisticated mapping technologies have become available. More recent surveys have incorporated digital data collection and processing, allowing survey data to be entered directly into computer software that can generate three-dimensional models of the cave geometry. These digital models provide a far richer representation of the cave's spatial structure than two-dimensional hand-drawn maps. They allow researchers to rotate and examine the cave from any angle to analyze the relationships between passages at different depths, and to overlay the cave model onto surface topography to understand how the underground system relates to the visible landscape above. Perhaps the most significant technological development in cave survey in recent decades has been the application of autonomous underwater vehicles, robotic systems capable of operating in the cave environment without a human diver, to the challenge of mapping passages that lie beyond the safe reach of conventional diving. The 1998-1999 Wakulla II project, which built on the foundation laid by the 1987 expedition, deployed an autonomous underwater vehicle designed specifically for cave exploration, a machine capable of navigating through cave passages, collecting sensor data, and returning to the entrance without continuous human guidance. This vehicle, developed through a collaboration led by Bill Stone and his team, represented a significant technical achievement, not only in terms of the engineering required to create a self-navigating robot capable of operating in the confined and complex environment of an underwater cave, but also in terms of the scientific data it was able to collect in portions of the cave system that no diver had previously reached. The vehicle used sonar acoustic ranging technology that measures distances by timing the reflection of sound waves from surrounding surfaces to create detailed maps of the cave walls and ceiling in passages too deep or too narrow for safe diver access. The data returned by this autonomous vehicle extended the known map of the Wakulla system significantly and provided researchers with their first detailed look at portions of the cave lying at depths and distances from the entrance that conventional diving equipment cannot safely reach. The passages documented by the vehicle in those deep remote sections of the cave showed a system continuing well beyond the limits of the survey, passages extending into the darkness beyond the vehicle's operational range. suggesting that the full extent of the system remained considerably larger than even the most optimistic estimates based on diver exploration alone. The challenge of understanding the three-dimensional geometry of a cave system also involves integrating the survey data with geological and hydrological information gathered from other sources. Researchers analyzing the Wakulla system have used water tracing studies, in which a harmless tracer dye is introduced into the groundwater at a specific location, and then monitored for its appearance at downstream springs and wells, to establish connections between portions of the cave and surface features that may be miles apart. These tracer studies have been enormously valuable in establishing the broad outlines of groundwater flow in the region, confirming connections between distant portions of the system that no diver survey has yet physically documented. One such connection, confirmed through water tracing before it was physically explored, is the link between the Leon Sinks sinkholes and Wakulla Spring itself. Tracer dye introduced into sinkhole pools at Leon Sinks was detected at Wakulla Spring after a travel time consistent with the distance and flow velocity of the underground passage connecting them, providing hydrological confirmation of a connection that cave divers subsequently explored and physically surveyed. The dye test came first, the map followed, passage by passage, dive by dive, across subsequent years of systematic exploration. The process of mapping an underwater cave system is, in an important sense, a process of making the invisible visible, of translating the experience of moving through a dark, water-filled passage into a spatial representation that can be studied, shared, and built upon by people who will never enter the cave themselves. Every survey measurement taken by a diver floating carefully in the darkness of the Wakulla cave adds one small element to a collective picture that no single person could ever assemble alone, a picture of an underground world whose true dimensions are still, even now, not fully known. This raises a question that follows naturally from the geography of the cave and the limitations of the survey, one that opens toward the future rather than the past. If 35 miles of passage have been mapped, and if water tracing and geological analysis suggest that the full system extends considerably farther, what does the unexplored portion of the Wakulla cave system actually contain, and what might it eventually reveal about the nature of the Floridan Aquifer as a whole? That question belongs to the future. But before reaching toward it, there is one more dimension of this underground world that has not yet been fully considered: the dimension of human imagination and cultural memory. The stories that people have told about the springs and the waters beneath Florida for as long as anyone can remember. Stories have always gathered around water. This is not particularly surprising when you consider the relationship between human communities and reliable water sources across all of recorded history. Springs, rivers, and lakes appear in the mythologies and folk traditions of cultures across every inhabited continent, not simply as practical resources, but as places of particular significance, locations where the boundary between the ordinary world and something larger or more mysterious seems thinner than it does elsewhere. The specific form these stories take varies enormously from culture to culture, shaped by local geography, local history, and the particular qualities of the water in question. But the tendency to find meaning in places where water emerges from the earth, where rivers gather, where still pools reflect the sky, this tendency appears to be nearly universal. The springs of Florida have attracted their share of stories across the long span of human presence in this landscape. It is important to be clear from the outset that what follows in this chapter belongs to the realm of cultural tradition and regional folklore, to the stories that communities have told about their landscape, rather than to the established findings of archaeology, geology, or hydrology. These traditions are a genuine and valuable part of the human history of this place, worthy of careful attention and respectful treatment. They are not, however, historical evidence in the documentary sense, and they should not be mistaken for factual accounts of events or phenomena that can be independently verified. With that understood clearly, it is worth acknowledging that the indigenous peoples who inhabited the Springs country of Florida for thousands of years before European contact lived within a world shaped by oral tradition, a way of transmitting knowledge, history, and cultural values from one generation to the next through carefully maintained narrative. The specific content of Appalachian oral traditions regarding the springs of their territory is not well documented in the historical record. In part because the catastrophic disruption of Appalachian society during the colonial period broke many of the chains through which such traditions would have been transmitted, and because European colonial observers who might have recorded them were not always attentive or well-positioned to do so accurately. What researchers and historians can say with some confidence is that fresh water, and particularly the remarkable springs of North Florida, occupied an important place in the landscape of indigenous life in this region. And that significant landscape features of this kind were rarely without cultural meaning in indigenous communities, whose relationship with their environment was deep and long-standing. To say more than this would be to venture into speculation that the available evidence does not support, and this documentary is not the place for that kind of speculation. The European colonial tradition brought its own stories to Florida's springs. Early Spanish accounts of the region frequently described the springs in terms that blended practical observation with a kind of wonder at the scale and character of what they encountered. The bottomless quality of the spring pools, the remarkable clarity of the water, the extraordinary abundance of fish and wildlife visible through the transparent surface. Some of these early accounts circulated in forms that gradually acquired embellishments. The spring that was said to have no bottom, the underground river that was said to extend all the way across the peninsula, the waters that were said to possess properties beyond the merely hydrological. The legend of the Fountain of Youth, one of the most enduring and widely known stories associated with Florida's colonial history, is sometimes loosely connected in popular culture to the remarkable springs of the region. The historical record does not support the idea that Juan Ponce de Leon came to Florida specifically in search of such a fountain. And historians studying this period generally regard the Fountain of Youth story as a later embellishment of the historical record rather than an accurate account of his actual motivations. Nevertheless, the story persists as a piece of cultural mythology that reflects the genuine quality of wonder that Florida's springs have inspired in outsiders encountering them for the first time. A wonder that, as we have seen, is not entirely without scientific justification, even if its legendary expression departs considerably from documented history. In the 19th and early 20th centuries, Florida's springs attracted a different kind of story. The stories of frontier naturalists, resort developers, and tourists encountering the extraordinary spring environments for the first time and struggling to describe them to audiences who had never seen anything comparable. Wakulla Spring, in particular, attracted considerable attention from writers and naturalists who found in its transparent water and remarkable wildlife a combination of natural beauty and quiet strangeness that seemed to demand some form of literary treatment. The spring's extraordinary clarity made it a natural subject for the early film industry. Wakulla Spring and its surrounding waters were used as a filming location for a number of Hollywood productions in the mid-20th century, including several Tarzan films and the 1954 science fiction film Creature from the Black Lagoon, whose underwater sequences were filmed in the spring's remarkably transparent water. The spring's appearance in popular culture through these productions added another layer to its cultural identity, overlaying the natural and historical significance of the place with the accumulated imagery of cinematic storytelling in ways that continue to shape how many visitors experience the spring today. Local folklore across the Springs region of North Florida includes the category of stories that might be loosely grouped as accounts of the spring's extraordinary depth. Stories circulated in various forms across many generations of local community tradition of springs that had no bottom, of objects lowered on long ropes that never reached solid ground, of underground connections stretching impossibly far beneath the Florida landscape. It is worth noting that these folk traditions, however imprecise in their specific claims, captured something genuinely real about the character of these places. The Wakulla Cave system is in objective fact a passage of extraordinary length and depth, extending far beneath the landscape, and the people who told stories about bottomless springs were reaching with the narrative tools available to them toward a truth that modern cave exploration has since confirmed in far more specific and measurable terms. This is perhaps one of the more interesting relationships between folklore and science, not a relationship of contradiction or mutual exclusion, but one in which the folk tradition perceives something real about the landscape and gives it a narrative form, while the scientific tradition eventually develops the means to describe that same reality with precision and documented evidence. The springs are not bottomless in the literal sense; they have measurable depths and documented extents. But they are, in the more poetic sense that the folklore was reaching toward, connected to something vastly larger than their surface appearance suggests, something that extends far beyond any single observer's ability to see or measure from the edge of the spring pool. The stories people tell about remarkable places are not simply errors or exaggerations waiting to be corrected by science. They are in their own way evidence of how deeply a landscape can capture human imagination, how persistently people return to questions that a place raises in them, and how the urge to explain the remarkable is a quality that connects the storyteller and the scientist across all the distances of method and vocabulary that separate them. The springs of Florida have inspired stories for as long as people have stood beside them. The stories will continue in new forms as long as the springs flow. What changes with the accumulation of scientific knowledge and careful exploration is the specificity and precision of our understanding, the ability to say not simply that something extraordinary lies beneath the surface, but to describe, in measured and documented terms, what that extraordinary thing actually is. And what it actually is, as the science of hydrology, biology, and earth science has gradually revealed, turns out to be something that matters far beyond the boundaries of any spring or any cave system, reaching into the daily lives of millions of people who have never stood beside a Florida spring and may never think to wonder where their water comes from. On a warm morning in almost any city or town across North and Central Florida, someone is filling a glass with water from a tap. The water is cold. It is clear. It has no taste that calls attention to itself. It is simply water, the background of daily life, taken without particular thought from a faucet, connected to a pipe, connected to a well, connected to the ground far below. The person filling the glass does not think about the Floridan Aquifer. They do not think about limestone or karst or groundwater recharge. They drink, they set down the glass, and they continue with their morning. And yet the water in that glass has traveled through an underground world of extraordinary complexity to reach them, moving through the pores and conduits of ancient limestone, carrying within it the chemical signature of its journey through the earths. Arriving at the tap as the end point of a hydrological cycle that may have begun as rainfall many years earlier and many miles away. The Floridan Aquifer provides drinking water for approximately 10 million people across Florida, Georgia, Alabama, and South Carolina. It is one of the most heavily used aquifer systems in the United States, supplying not only domestic drinking water, but also water for agriculture, which accounts for a very large proportion of total groundwater withdrawals, and water for industrial and commercial uses across a broad region. The agricultural operations of Florida and adjacent states, which produce a substantial portion of the vegetables, citrus, and other crops consumed across the eastern United States, depend significantly on the aquifer for their irrigation water during the dry season when surface water availability is limited. The aquifer's capacity to supply this water is not unlimited, and the relationship between water demand and aquifer health has become one of the central environmental and resource management challenges across the region. Unlike a reservoir or a water tank, which has a fixed and visible capacity that decreases as water is withdrawn, the aquifer is a dynamic system. It is continuously being recharged by rainfall entering through the recharge zones, and the water available at any given time represents the balance between recharge and discharge. When withdrawals from the aquifer through wells, springs, and natural discharge exceed the rate of recharge, the water level in the aquifer declines, and the consequences of this decline ripple through the entire hydrological system. One of the most visible indicators of aquifer health in Florida is the flow rate and water level of the springs. Springs are, in a very direct sense, the aquifer's expression of its own condition. When the water table in the aquifer is high, spring flows are strong, and the water level in the spring pool is correspondingly elevated. When the water table declines, whether through drought, heavy groundwater withdrawal, or a combination of both, spring flows decrease, and in the most extreme cases, springs can reduce their flow substantially from historical levels. Researchers monitoring Florida's springs over the past several decades have documented significant declines in flow at many springs across the state, declines that represent a meaningful change in the ecological character of these environments, and that reflect the cumulative effects of groundwater use and changing rainfall patterns across the recharge zone. Wakulla Spring itself has not been immune to these pressures, and research conducted at the spring over many years has documented changes in water quality and flow characteristics that reflect broader conditions in the aquifer system upstream. Water quality within the aquifer is a concern that extends beyond flow rate. The Floridan Aquifer is recharged primarily through the karst terrain of North Florida and adjacent areas, a landscape where rainwater enters the ground quickly and with relatively limited opportunity for filtration by the soil layers that would, in a non-karst terrain, provide a degree of natural purification. In karst systems, water that enters a sinkhole or a fracture in the limestone can move directly into the aquifer with relatively little time in contact with the soil, meaning that pollutants present at the surface can, in some cases, enter the groundwater relatively quickly and travel considerable distances through the conduit system before emerging at a spring. Agricultural activities across the recharge zone have historically been among the significant sources of nitrate contamination in the Floridan aquifer. Fertilizers applied to crops and lawns, animal waste from livestock operations, and septic system discharges can all contribute nitrate, a form of dissolved nitrogen, to the groundwater. Nitrate is not immediately toxic to most people at the concentrations found in many aquifer areas, but it is highly significant as an ecological indicator because elevated nitrate levels in spring water promote the growth of algae in the spring run, the clear stream that flows from the spring pool downstream through the surrounding landscape. The changes associated with elevated nitrate, the growth of algae on the spring bottom where once clear sand and rock were visible, the reduction in the clarity of the water that has historically defined Florida's springs as among the most transparent natural water bodies in the world, represent a genuine ecological transformation of these environments, one that researchers have studied with growing concern over several decades. The biology of the spring ecosystem is directly connected to the quality of the water flowing through it. The animal communities of Florida's springs, including the manatees that gather in spring runs during cold winter months, drawn by the constant 68-degree temperature, the large populations of mullet bass and other fish species that inhabit the spring pools, and runs the remarkable diversity of invertebrates and plants that characterize a healthy spring environment, are all supported by and are sensitive to the specific chemical and physical conditions of the spring water. The Manatee connection to Florida's springs is a particularly well-known example of how the aquifer's constant temperature supports wildlife that would otherwise struggle in Florida's variable winter climate. West Indian manatees, which are vulnerable to cold stress and can suffer serious physiological harm when water temperatures drop below certain thresholds, rely on the warm, constant water of Florida's springs as thermal refuges during cold winter months. Major springs like Wakulla, Crystal River, and Blue Spring serve as gathering points for manatees during cold snaps, with populations sometimes numbering in the hundreds at the most populous springs. The health and flow of these spring systems is therefore directly tied to the survival and recovery of the Florida manatee population, a connection that illustrates, in very concrete terms, how groundwater management and wildlife conservation are inseparable in Florida's ecological context. The aquifer also serves as a geological archive of significant scientific value. The water stored within the Floridan aquifer has been studied for its isotopic composition, particularly the ratios of different isotopes of hydrogen and oxygen, which vary depending on the temperature and conditions under which precipitation fell and entered the ground. These isotopic ratios, measured with precision in water samples from wells and springs across the aquifer system, allow researchers to reconstruct information about the historical climate of the recharge area, how temperatures and rainfall patterns have changed over the time period represented by the groundwater currently stored in the aquifer. Groundwater from deep portions of the aquifer, water that entered the ground many thousands of years ago under the climate conditions of the late Pleistocene, carries an isotopic record of those ancient conditions, providing researchers with a window into climate history that complements and extends the records available from ice cores, tree rings, and other paleoclimatic archives. The aquifer is not only a water supply, it is also a record of the climate that created it, written in the chemical language of dissolved atoms and molecular ratios. The convergence of water supply ecological support, paleoclimatic record, and geological significance makes the Floridan aquifer one of the most scientifically important natural systems in North America, and one whose health and continued functioning matter at a scale that extends far beyond the boundaries of any single state or region. The scientific community's understanding of the aquifer continues to deepen with each new generation of monitoring technology, each new analysis of water chemistry, and each new survey of the cave systems that give the aquifer its most dramatic physical expression. And yet, despite decades of research, despite thousands of dives and hundreds of scientific publications and the most sophisticated monitoring technology ever applied to groundwater systems, the full extent of the Floridan aquifer's cave systems remains, as it has always been, largely unknown. Beyond the surveyed passages of the Wakulla sink system, beyond the reach of the autonomous vehicles that have probed the deepest accessible sections of the cave, the passages continue, extending through limestone that no instrument or diver has yet reached, connecting to portions of the aquifer that remain entirely undocumented, carrying water through a landscape that has never been observed by any human eye. The frontier of the unknown in the Floridan Aquifer does not lie at the edge of an ocean or at the summit of an unexplored peak. It lies beneath the ground, accessible only through a crystal-clear pool in a North Florida forest, reached only by descending slowly through the water, following a guideline through the dark, and gradually approaching the boundary between the known and the unknown. That frontier and the future of exploration within it is where this journey leads next. There is a particular kind of humility that comes from standing at the edge of something genuinely unknown. Not the dramatic humility of a person confronting a vast ocean or a towering mountain range. Experiences that are large but visible, whose dimensions can at least be sensed from the outside, even when they cannot be fully measured. The humility that comes from the unmapped passages of the Floridan Aquifer is quieter and more particular than that. It comes from the knowledge that the unknown does not announce itself with visible grandeur. It simply continues in the dark, beneath the limestone, beyond the last survey station, beyond the reach of the last guideline, as it has continued for millions of years, entirely indifferent to whether anyone ever reaches it or not. The documented portions of the Wakulla Spring cave system represent, by the best current scientific estimates, only a fraction of the total cave system that connects the recharge areas of North Florida to the spring at Wakulla and to the other springs and groundwater discharge points scattered across the region. The passages that have been surveyed, those 35 and more miles of documented underwater tunnel, were reached through thousands of individual dives conducted across several decades by some of the most experienced cave divers in the world. Using equipment and techniques that represent the current practical limits of what human beings can safely accomplish in an underwater cave environment. And yet the water emerging at Wakulla Spring carries within it evidence of passages that no diver has reached, the dissolved mineral content of the water. Its temperature, its biological components, and the results of water tracing studies all suggest connections to portions of the aquifer that lie well beyond the current boundary of exploration. The cave does not end where the surveys end. It continues, as the groundwater continues, through passages that remain entirely undocumented and in many cases physically inaccessible to the technologies currently available. The practical limits of cave diving exploration are defined by several converging factors. Time is perhaps the most fundamental. The time available on a given breathing gas supply determines how far a diver can travel from the entrance before the reserve required for the return journey is exhausted. Technical diving techniques, including the use of rebreather systems that recycle exhaled gas and the deployment of staged gas supplies cached at intervals along the cave passage, have extended the operational range of cave divers significantly beyond what was possible with the earliest open-circuit scuba equipment. But even with the most advanced rebreather technology currently available, there are limits to how far a single diver can travel from the entrance and return safely, limits imposed by the physical constraints of the equipment and the physiological constraints of the human body operating at depth and under pressure. Depth presents its own set of challenges. As a diver descends deeper into the cave, the ambient pressure of the water increases correspondingly, and this increased pressure affects the behavior of the breathing gases in ways that become progressively more significant and more demanding to manage. The deeper sections of the Wakulla cave system, portions that have been reached by divers using the most advanced technical equipment available, extend to depths that require very careful management of breathing, gas composition, decompression obligations, and dive time to maintain safety. These deep sections represent not just the geographic frontier of the cave survey, but also the physiological frontier of what the human body can safely experience in this environment. It is in response to these limitations, the limits of human physiology and the limits of breathing gas endurance, that the role of autonomous underwater vehicles in cave exploration becomes most significant. A robotic system does not breathe. It does not accumulate decompression obligations. It does not experience the cognitive effects of breathing gases under pressure. A well-designed autonomous underwater vehicle can, in principle, travel farther into a cave, remain there longer, and reach depths that no human diver could safely access, providing survey data and visual documentation from portions of the cave system that would otherwise remain entirely beyond reach. The development of vehicles capable of navigating the complex, three-dimensional environment of an underwater cave is, however, a significant engineering challenge. Unlike the open ocean, where an autonomous vehicle can navigate by reference to GPS signals and broad acoustic positioning systems, the inside of a cave provides none of these navigational references. The vehicle must navigate using its own onboard sensors, acoustic ranging systems, inertial measurement units that track movement and orientation, and sophisticated software that integrates these data streams to maintain an accurate understanding of the vehicle's position within the cave. The passages of the Wakulla system present additional challenges specific to this environment. The presence of halocline layers in some portions of the cave, where fresh groundwater from the aquifer meets saline water intrusion from the coast, creates optical distortions that can affect camera-based navigation systems. Tight passages, abrupt changes in ceiling height, and the fragility of the cave's silt layer, which can be disturbed by the water currents generated by a vehicle's propulsion system, reducing visibility just as it does when disturbed by a diver's fins. All represent engineering problems that require thoughtful solutions. Researchers and engineers working at the intersection of underwater robotics and cave science have made significant progress on these challenges in recent years. The vehicles deployed in the 1998-1999 Wakulla II project, while remarkable achievements for their time, represented early iterations of what has become an increasingly sophisticated field of engineering. Subsequent generations of autonomous underwater vehicles have incorporated improved navigation algorithms, better sensor systems, and more refined propulsion designs that reduce the disturbance of the surrounding water, making them progressively better suited to the specific demands of cave exploration. Future expeditions to the Wakulla system. Incorporating the most advanced autonomous vehicle technology currently being developed have the potential to extend the surveyed map of the cave significantly, probing deeper passages, documenting portions of the system that have never been physically reached, and providing the scientific community with data about the aquifer's structure and extent that cannot be obtained by any other means. The planning and preparation for such expeditions is a long and careful process involving collaboration between cave diving specialists, underwater robotics engineers, hydrologists, geologists, and biologists, each bringing a different perspective on what questions need answering and what the data returned by such an expedition might reveal. The scientific questions driving this exploration are not simply geographical. They are not merely about establishing how many miles of passage the cave system contains, though that is certainly one dimension of the inquiry. They are also questions about how the aquifer functions as a hydrological system, how water moves through the conduit network, how different portions of the system connect, how the cave responds to changes in recharge and discharge over time. Understanding the detailed structure of the cave system is directly relevant to understanding how the aquifer functions as a water supply, how groundwater moves through it, how contaminants introduced at one location might travel to another, how the system responds to drought or to changes in land use in the recharge zone. There is also a dimension of pure scientific discovery in the unexplored portions of the cave, the biological communities that may inhabit the deep, remote sections of the system, the geological features preserved in passages that have never been disturbed by any human visitor, the hydrological connections between distant portions of the aquifer that remain theoretical until physically confirmed by survey. Each extension of the known map adds not only geographical knowledge, but scientific understanding of a system that remains, in important ways, genuinely and honestly unknown. The researchers and explorers who work at this frontier do so with a clear awareness of the scale of the task relative to the resources available to accomplish it. The Floridan Aquifer is enormous, 100,000 square miles of limestone platform, threaded through with conduits and passages whose total extent is entirely undetermined. The surveyed portions of the Wakulla cave system represent a beginning, a significant and hard-won beginning, built on decades of careful work by many dedicated people, but a beginning nonetheless, in relation to the total system that the aquifer almost certainly contains. This is not a source of frustration for the researchers involved in this work. It is rather one of the qualities that makes the work genuinely meaningful, the knowledge that each dive, each robotic survey mission, each water quality sample and tracer test adds a small but real increment to human understanding of a system that has been here quietly flowing for far longer than human curiosity has existed to ask questions about it. The unknown is not a problem to be solved and set aside. In the Floridan Aquifer, the unknown is the condition that makes the work worth doing. The assurance that there is always more to learn, always more passage beyond the last survey station. Always more water moving through the limestone towards springs that may or may not yet have been identified at the surface above. There is a moment, sometime in the course of learning about the Floridan Aquifer, when the scale of what is at stake shifts from the abstract to the very personal. It might come while standing beside Wakulla Spring, watching the clear water rise from somewhere far below and thinking about the tens of millions of people whose daily lives depend on the continued health of the system producing that water. It might come while reading about the declining flow rates at Florida's springs and understanding that these changes reflect real shifts in the aquifer's condition, shifts with consequences that extend well beyond the aesthetic loss of a somewhat less transparent spring pool. It might come in a more ordinary moment, in the simple act of filling a glass from a tap and allowing the thought to follow the water backward through the pipes and wells and limestone to the place where it actually originates. Whenever it comes, the realization carries a quality of quiet urgency that is different from the urgency of more dramatic environmental concerns. The Floridan Aquifer does not burn. It does not collapse in a single visible catastrophe. It changes slowly, in response to pressures accumulated over years and decades, and the changes it experiences are often invisible to anyone not specifically looking for them. This invisibility, which is, as we have seen throughout this documentary, the aquifer's most fundamental characteristic, makes it both easier to overlook and, in a certain sense, more important to understand. Freshwater is among the most essential resources that any human community requires, and the quality and reliability of that freshwater supply shapes the possibilities available to every person who depends on it. The 10 million or more people who draw drinking water from the Floridan Aquifer are connected to this underground system in the most direct and practical way possible. Through the water in their bodies, the water in their food, the water that sustains the crops, the livestock, and the ecosystems that support their lives. The health of the aquifer is not an environmental concern separate from the concerns of daily human life. It is one of the foundations on which daily human life in the American Southeast is built. The conservation of the aquifer requires attention to several interconnected dimensions of the problem. The first is the management of groundwater withdrawals, the balance between the rate at which water is pumped from the aquifer and the rate at which it is naturally replenished through recharge. Water management districts across Florida have developed systems of permitting and monitoring designed to prevent withdrawals from exceeding sustainable levels. Levels at which the aquifer can continue to provide water indefinitely without experiencing the kind of long-term decline that would ultimately compromise its ability to serve the communities depending on it. This is, in practice, a challenging balance to maintain. Population growth across Florida and adjacent states has driven increasing demand for groundwater over many decades, and the pressure on the aquifer from municipal, agricultural, and industrial users has grown correspondingly. Water managers must navigate the competing demands of a growing population while maintaining the aquifer conditions necessary to sustain spring flows, support aquifer-dependent ecosystems, and preserve water quality for future users. The decisions made in this balancing process have implications that extend across generations. The aquifer's response to changes in withdrawal rates and recharge conditions plays out over timescales measured in years and decades rather than days or weeks. The protection of recharge zones is a second critical dimension of aquifer conservation. The karst terrain of North Florida, where rainfall enters the aquifer most readily through sinkholes and fractures in the limestone, is the foundation of the aquifer's ability to replenish itself. Land use practices in the recharge zone, the types of development, agriculture, and land management that occur in areas where rainwater flows directly into the ground, directly affect both the quantity of recharge the aquifer receives and the quality of the water that enters it. Conservation of natural vegetation cover in the recharge zone supports aquifer health in multiple ways. Forests and wetlands slow the movement of rainwater across the surface, allowing more of it to infiltrate into the ground rather than running off into streams and rivers. And the biological activity of soil organisms in natural vegetation communities helps filter water as it percolates downward. The protection of sinkholes, which serve as direct conduits between the surface and the aquifer below, from filling, paving, or contamination, is particularly important, since these features represent points where the aquifer's protective cover is most limited and where surface contamination can enter the groundwater most readily. Springs protection efforts across Florida have grown significantly in recent decades as the documentation of spring flow declines and water quality changes has accumulated. State and local governments, water management authorities, conservation organizations, and research institutions have collaborated on programs designed to reduce nitrate loading in the aquifer, restore natural hydrology to spring runs, and manage the spring's ecosystems in ways that support the biological communities they contain. These efforts involve complex coordination across many different stakeholders: farmers, municipalities, developers, conservationists, and researchers, whose interests and priorities do not always align naturally and whose collaboration requires patient and sustained negotiation. The biological significance of Florida's springs extends well beyond the cave-adapted species discussed earlier in this documentary. The spring runs, the clear, constant-temperature streams that flow from the spring pools through the surrounding landscape toward rivers and ultimately the sea, support some of the most productive and distinctive freshwater ecosystems in North America. The combination of constant temperature, high clarity, and rich mineral content of the spring water creates conditions that support extraordinary densities of aquatic vegetation, which in turn provides habitat and food for diverse communities of fish, invertebrates, reptiles, birds, and mammals. The manatees that gather at Florida's springs in winter have already been mentioned, but the ecological significance of the springs extends through many other species as well. Limpkin birds, which feed primarily on apple snails found in spring runs, are closely associated with spring ecosystems across North and Central Florida. The Florida gar, the long-nosed gar, various species of sunfish and bass, and numerous other fish species inhabit spring runs in numbers that reflect the extraordinary productivity of these environments. Freshwater turtles, river otters, wading birds, and numerous other species complete the spring run ecosystem, a community of life supported, ultimately, by the clear, mineral-rich water rising from the aquifer below. The springs are also places of significant recreational and cultural value to the human communities that live near them. Swimming, snorkeling, kayaking, and nature tourism at Florida's springs contribute substantially to local economies and provide residents and visitors with experiences of natural beauty that are genuinely rare and that depend entirely on the continued health of the aquifer system, producing the spring water. The economic value of healthy springs to local businesses, to tourism, to the fishing and recreation industries, provides a practical framework for conservation that complements the ecological and scientific arguments for protecting the aquifer. The research conducted at Wakulla Spring and other major springs of the Floridan Aquifer system has contributed to scientific understanding that extends well beyond Florida's borders. The hydrological processes studied in the Floridan system, the dynamics of conduit flow in karst aquifers, the behavior of spring systems under varying recharge and withdrawal conditions, the chemistry of groundwater in limestone formations, are relevant to the study and management of similar systems in other parts of the world. Karst aquifers provide water to substantial portions of the global population, and the insights gained from careful study of the Floridan system have informed the understanding and management of comparable systems in Europe, the Middle East, and elsewhere. In this way, the underground world beneath Florida, so local in its geography, so specific in its geology, so particular in its biological communities, connects to something much larger than itself. The knowledge gained from studying the Floridan Aquifer belongs not only to the scientists who produced it or the communities who depend on the water it contains, but to a broader human understanding of how freshwater moves through the earth, how limestone shapes the landscape over geological time, and how the invisible processes beneath the surface quietly determine the character of the world above. The aquifer does not ask to be understood. It does not require human attention or human appreciation to continue its work. The water will flow through the limestone whether anyone studies it or not, whether anyone maps the caves or measures the spring flows or monitors the water chemistry or protects the recharge zones. The aquifer has been doing all of this, flowing, dissolving, recharging, discharging for millions of years before any human being arrived to notice it, and it will continue in whatever form the changing climate and geology allow long after the current generation of researchers and resource managers has been replaced by others. But the communities that depend on the aquifer and the ecosystems that it supports do not have the luxury of geological patience. They exist within human timescales, within the span of individual lives, of political cycles, of generational change. The decisions made now about how to manage, protect, and study the Floridan Aquifer will shape the water supply, the ecological health, and the scientific understanding available to the people who will stand beside Florida's springs 50 or 100 years from now. What those future visitors will find when they look into the clear water of Wakulla Spring, whether the spring still flows with the abundance and clarity it has maintained across human memory, whether the cave below still harbors the extraordinary biological communities that have evolved within it across thousands of years, whether the water still rises cool and constant and clean from the ancient limestone below, depends in no small part on the choices being made today by people who may never see the spring themselves, but whose decisions reach down through the soil and the limestone to the hidden rivers below. The morning comes slowly to the cypress forest around Wakulla Spring. It arrives the same way it always has, first as a softening of the darkness in the canopy above a gradual lightening that moves through the hanging moss before it reaches the water. A pale suggestion of blue and grey along the eastern edge of the forest, where the trees thin slightly and the sky begins to open. The birds start quietly, as they always do, a single note somewhere in the distance, then another closer by, then gradually the full, unhurried morning chorus of a North Florida woodland settling into the familiar rhythms of another day. The spring pool appears before you in the early light as something between a mirror and a window. The surface is still, or nearly still, stirred only by the continuous, gentle upwelling of water from somewhere far below that creates a barely perceptible shimmer at the center of the pool. The cypress trees at the edges are reflected in the surface with a clarity that doubles the forest, creating the impression of a second woodland growing downward beneath the water, perfectly symmetrical and perfectly silent. If you sit beside this spring long enough, the light changes. The pale grey of early morning gives way to something warmer, the first direct sunlight reaching down through the canopy in long, quiet shafts that catch the mist still hanging over the water and give it a quality of luminosity, as though the air itself is faintly lit from within. The reflections on the spring surface shift and soften. The water below becomes visible, the pale limestone bottom, the slow drift of a fish turning lazily in the current, the dark opening of the cave entrance at the deepest point of the bowl, barely visible from the surface as a shadow within a shadow. We have traveled a considerable distance together to arrive back at this moment beside the spring. We have followed the water from its origins as rainfall falling across the recharge zones of North Florida, watched it seep through the soil and descend through fractures in the limestone, traced its slow journey through the conduits and passages of the Floridan Aquifer. We have descended, in imagination and in the company of those careful and patient explorers who have done so in fact, through the entrance of the cave below Wakulla Spring and moved through the darkness of one of the longest underwater cave systems in the Americas. We have visited the geological past, the warm Eocene seas where the limestone was assembled, grain by grain and organism by organism, across millions of years of marine accumulation. We have walked beside the springs with the people who knew them longest, the Paleo-Indian hunters of the Pleistocene. The Appalachian communities of the pre-colonial period, the naturalists and explorers of the colonial and early American eras, who stood at this same edge and found themselves reaching with whatever vocabulary was available to them towards some description of what they were seeing. We have met the cave divers who descended into the darkness with guidelines and survey slates, and the particular combination of patience and precision that this work requires, Sheikh Exlai, who spent decades mapping the underground rivers of Florida with a methodical care that transformed the scientific community's understanding of these systems. Bill Stone, whose engineering mind and explorer's temperament drove the development of the technologies that extended human reach into passages that conventional equipment could not access. And the many other divers, less individually celebrated, but equally essential, whose collective work across many years assembled the map that now documents more than 35 miles of the Wakulla cave system's extraordinary extent. We have encountered the organisms that have made the cave their permanent home, the pale crustaceans with their vestigial eyes, the unpigmented salamanders navigating the aquifer by chemical sense alone, the microbial communities drawing their energy not from sunlight, but from the chemistry of rock and water in the permanent dark. These creatures know nothing of the surface world above the limestone. Their universe is the water, the stone, and the slow chemical gradients of the cave environment, a world that has been stable for far longer than the surface world that most living things inhabit. We have considered what the aquifer means not only as a geological formation or a scientific subject, but as the practical foundation of life across an enormous region. The water in the glass, the crops in the field. The manatees gathered in the warm spring run on a cold January morning, the city and the farm and the forest, all connected through the invisible pathways of the karst to the same ancient limestone formation quietly doing its work beneath the Florida landscape. And we have stood as patiently as we are able at the frontier of the genuinely unknown. The passages beyond the last survey station the portions of the aquifer that no instrument has yet reached. The biological communities that may inhabit the deepest and most remote sections of the cave system in conditions that no researcher has yet been in a position to document. The unknown portions of the Floridan Aquifer are not a mystery in the dramatic sense that the word sometimes implies. They are simply the part of the story that has not yet been told, the chapters still being written slowly and carefully by researchers and explorers working at the edge of what current knowledge and technology allow. What strikes you sitting beside Wakulla Spring on this quiet morning is how little the spring itself reflects the extraordinary complexity of what lies beneath it. The surface is calm, the water is clear, the cypress trees stand in their reflections. The birds continue their unhurried conversation in the canopy above. Nothing in the visible scene announces that this peaceful pool is the entrance to one of the great underground labyrinths of the American continent, that beneath this still surface lies a network of passages extending for many miles in multiple directions through ancient limestone, carrying water that fell as rain perhaps years ago in the highlands of North Florida toward the surface of this particular spring in the middle of this particular forest. The spring simply rises, as it has always risen. There is something profoundly calming about this quality of constancy. In a world that changes with extraordinary and sometimes disorienting speed, where landscapes are transformed in years, where weather patterns shift across decades, where the familiar becomes unfamiliar with a regularity that can feel exhausting, the aquifer beneath Florida moves according to rhythms that operate on an entirely different scale. The water that fills the Wakulla cave system today began its journey through the limestone long before any of the buildings visible from the nearest road were built, long before the road itself was laid, long before the landscape above was organized into the form it takes today. The geological processes that created the limestone, the shallow Eocene, sees the accumulation of marine organisms, the slow compression of calcium carbonate into solid rock, operated across timescales so vast that human history, with all of its apparent complexity and turbulence, occupies within them something smaller than the finest line a surveyor's pencil can draw on a map. The karst dissolution that carved the cave passages, that patient, slow, chemically precise process of rainwater dissolving limestone molecule by molecule, has been proceeding for millions of years and will continue proceeding at its own unhurried pace, regardless of anything that happens at the surface above. This is not a diminishment of human significance. It is rather a kind of perspective, a reminder that the world was enormously complex and quietly extraordinary long before anyone was here to notice it, and that the act of noticing, of understanding, of carefully studying and thoughtfully protecting what exists here is one of the most meaningful things a human community can do with the brief time it has in any particular place. The aquifer beneath Florida does not need our admiration to continue its work. The cave below Wakulla Spring does not require our curiosity to maintain its extraordinary structure. The organisms living in the permanent dark of the cave conduits do not depend on our awareness of their existence to continue their patient, adapted lives. These things simply are ancient and patient and continuing, independent of any human witness. But we are here, beside the spring, in the morning light, and in being here, in taking the time to learn something about what lies beneath this calm surface, about the geology and the hydrology and the biology and the human history of this extraordinary place, we have entered in the only way available to us, into a relationship with something that has been here for an almost incomprehensibly long time. The guideline that connects every cave diver to the entrance of the Wakulla cave, that continuous thread of physical connection between the explorer and the world of daylight above, is, in its own way, a useful metaphor for the relationship between human understanding and the natural world it seeks to know. We extend our awareness carefully into the unknown, measuring what we find, recording what we observe, returning with what we have learned to share it with others. And always, at the end of the dive, we follow the guideline back toward the light. The light, this morning, has reached the full surface of the spring now. The mist has burned away in the warmth of the rising sun. The spring pool is brilliant and transparent, its extraordinary clarity fully visible in the direct morning light, the pale bottom, and the dark cave entrance, both visible simultaneously. Connected by the column of water that has been rising through this opening for longer than any human tradition of memory reaches. In the trees above, a great blue heron stands motionless at the water's edge, watching the surface with the unhurried patience of a creature that has no need to be anywhere else. The water continues rising from below. It will continue rising through the afternoon, through the evening, through the night that follows, and through all the mornings that come after this one, carrying within it the chemical memory of its long journey through limestone, the dissolved record of an underground world that most people will never see and never think to wonder about. Arriving at the surface as it has always arrived, quietly, constantly, patient beyond any human measure of patience. Long after every diver has returned to the surface, the silent rivers beneath Florida will continue their patient journey through ancient limestone, quietly shaping the land above, one drop at a time. Thank you for spending this quiet evening with us, exploring one of North America's most extraordinary hidden landscapes. The Floridan Aquifer and the underwater labyrinth of Wakulla Spring will continue their ancient work long after this night has passed and the morning has come again. We hope this journey through the hidden waters beneath Florida has given you something peaceful to carry with you into sleep.